Okay, welcome. So assignment 6 has been uploaded. As you can see, I did it twice. Deadline is next Monday. Assignment 5 deadline used to be today, but as discussed, we extended it to Friday for those students who need this. Still, same thing, same words. Please try your best to hand in the homework earlier. Okay, and the midterm, this is the same message. So far, I have received some emails telling me that you cannot come to face-to-face. I'm still waiting for more emails because I would like to deal with all this together rather than sending 10 individual emails. Okay, so for those of you who cannot attend with a valid reason, okay, so this applies to all of you. So if you really cannot come, you can show that, you can prove that you cannot come. I will arrange an online exam for you. But I'm very strict about this. You need to make sure I can see you all the time. And you need to show me the room. I need to be able to check your environment. There will be a guideline for you. I developed some guidelines before, and I will share with you in due course. Okay, but meanwhile, if you plan to take my online exam, please make sure you prepare for this. I need a good camera. I need to be able to, so usually you use your phone. You need to use your phone to show me the environment. You have to position your phone carefully, and then you use your computer to read my my questions. Okay, and if there's anything we don't like, we are going to tell you during the exam. Okay, so I hope this is understandable. As usual, my aim is to run a valid and fair assessment. Okay, and something new is here. The coverage is updated here. So we are going to cover chapters 1 to 7. And part of chapter 7. Okay, so this is, let me see, this is 7.4, right? Is it 7. Let me see, sorry. Yes, 7.4. So this is 7.4. Okay, so I will be able to finish this today. Okay, as you know, I didn't follow the sequence of chapter 7. That's because you will know very soon why I do it this way. Okay, is it okay with you about this midterm exam? Is it clear? Okay. Okay, no response means it's okay. All right. Last lecture. Let's begin with last lecture. We have two issues arising. One is about this latent heat, the dependence of that. So who asked this question again? But anyway, this question is actually related to the assignment, assignment 6. As you remember, in the class, I did a simple case, and in the assignment, you are asked to do a general case. In that general case, you are asked to take the derivative along the phase boundary. Okay, if you haven't seen the problem, you might not, this might not make too much sense to you. But remember, we get the closest Clapeyron equation. Okay, so we get this dB dt. And the question is about the dependence on of the latent heat on other parameters. So there in the class, I simply say L is independent of temperature, but what I really meant is L is a constant, this latent heat, L is a constant. Okay, in the, this is in the lecture, I did this. So I can integrate this very quickly for you. And in the assignment, you are asked to do something, and you will see what we assume the dependence of L to be. Okay, so there, I think you will. So basically, the question, the explicit question is: do we assume L to be independent of P as well? But when you do the assignment, you will see you do not assume this. Okay, you do not assume L to be independent of pressure. You do not assume L to be independent of temperature either. So when you develop an equation to differentiate along the phase boundary, this is basically this is a hint for you. You are going to do a treatment that do not assume either of these dependence. Okay, so this is one issue, and the other issues is again related to this. So in the lecture note, I wrote something like this. So basically, it's here, this line. This is from, I believe, it's from a different student or different group. It's a bit earlier. Yeah. Okay. So here, this is following Blundell and Blundell. Okay, so we developed this by using the specific quantities. And then when I switch to here, I say we multiply by the system size. Okay, so you can only do that if the system size is the same. Okay, that is to say you can use this to investigate the situation when you have, for example, 1 kilogram of water freezes into 1 kilogram of ice. Okay, or 1 mole of a particular substance changes to the phase completely, and that will allow you to calculate this slope as well. And that is to say, if you take it this way, basically it also implicitly imply some quantity that depends on the system size. Okay, so here is basically saying that if I know that I'm talking about 1 mole of the material, I can just write it in terms of the extensive quantity. Okay, so actually, if you look at this way, it doesn't really carry much new information. So we developed this by looking at the equilibrium. We are talking about an equilibrium, right? So that's why if I have some quantity of liquid in equilibrium with some quantity of gas, then I can write down this line here if I know the amount of quantity. Okay, at equilibrium we have this. So here another way to look at this is to look at it a little bit dynamically. I will say, okay, I have 1 kilogram of material, or 1 mole of particular material changes from phase A to phase B, then I can have this equation. Okay, so these are the two issues. Okay, so this is which page? Page number will always be a bit different. So this is I won't write this down. Okay. All right. Is it okay? All right. So let's continue. So last time I began to talk about open system. So what did I present? I started by introducing the notion of chemical potential. Okay, so I begin by writing down the first law. So this is still okay. I will start from here. A little bit of from last lecture. I introduce mu. This is the chemical potential. We did that from writing down the first law for the open system. So we are still talking about PV. So this is an open PV system. And later I'm going to close the system again, but I'm going to talk about non-PV system. And that would be cool because I will be able to tell you some stories on how to cool things down to very low temperature. So this is something very close to my research. It will be very nice to share with you. Okay, so let's look at the open system first, and then link it to phase transition. Okay, what is the first law for this? The first law, you will have the usual TDS. Now, I can still work on my PV system. So this is a work term. And because I'm allowed to introduce particle, in principle, if the particle brings in additional energy, now you know what that is. That is related to this notion of chemical potential. I will be able to increase or modify my internal energy. Okay, so this is the modifier's first law. And then from here, we can extract the usual differential again. So I'm going to write down only one, which is new to you. So we can write, what is this mu? For this particular thermodynamic potential function, this will be this quantity. And then you just keep the other variable constant. Okay, so we have done all this, and in the end, we use the second law again to discuss equilibrium. But now the equilibrium is related to the diffusion of the particle, the flow of the particle. Okay, so just before the end of last lecture, we know that if we have diffusive, let's say we have a system that we can partition it. And for last time, I think I set the partition to be rigid. You can do it very generally by having the partition to be movable. Then you will see the effect of maintaining a mechanical equilibrium. Okay, and that is the requirement is the pressure on each side, on both sides, must be equal. Okay, this is something you did in the assignment. But last time I made the partition to be rigid, but I allowed the particle to move from one to the other. Maybe I have a membrane that allows the particle to move. So that is a diffusive equilibrium. So I have system 1, system 2. And the requirement for that is mu1 is the same as mu2. Okay, and if you have different mu, if mu2 is greater than mu1, for example, then you can drive the flow of particles. So the equilibrium condition is this, and the flow of particle is driven by the difference in mu. Okay, so that is that actually already gives you some feeling about the word chemical potential. Okay, so today I want to move a little bit further by having a system with more than one type of particle. So if you have more than one type of particle, more than one type of particle, when you have this situation, the chemical potentials might not be the same to begin with. So you can you have to include all of them. Okay, so if you have m types of particle, more than one, if you have m types of particle, the first law will become like this. You have to sum over all these mu I d n item, where I takes from 1 to m, right? This is simply a label telling you which type of particle you are talking about. And the chemical potential in this case will be mu I, partial derivative with respect of u with respect to capital N sub I, and then you keep everything else constant. You keep entropy constant, volume constant, and all the n's constant. or the n k, which is not the same as I constant. Okay, so for example, if you take a piece of semiconductor, you will see very readily this kind of picture. In a semiconductor, I think even if you haven't taken solid state physics, you might have heard about the notion of hole, electron and hole. And there you treat your thermodynamic system, namely your semiconductor, to have two different types of particles. So you have electrons and you have mu sub e electron and you have mu sub h for the hole. And that is very common. Okay, so you see this expression, but what we really want to have, it would be really nice to be able to integrate U, to see the dependence of U on all these variables. Okay, so it would be really nice to get U in terms of all these variables as V, N, and I's. Okay, and usually you will do this by integration. But actually, there's a very nice trick here. And this is, so you can get this expression by using Euler's theorem. Okay, so what is Euler's theorem? And this theorem, I'm sure you have seen this before. You've seen it probably in one of those STOT classes. Okay, so let me remind you, if I have a function like this, okay, this is Euler's theorem. I'm going to write a general function. It can be longer than this. So if I have this kind of scenario, lambda y, lambda z, then f is very simple. F, this function will simply be x partial f partial x, y, everything else constant. Where are we? Okay, you have seen this before, right? So this f, this is a homogeneous function of degree k. Now this k turns out to be 1, so this is a homogeneous function of degree 1. Okay, so this is so f, if you have this, this is terminology. So if f of alpha is lambda, I want a different notation, and I don't want to write x, y, z anymore. I'm just going to treat it as a vector. If this is true, okay, then f is a homogeneous function of degree k. Okay, so we have a simple situation which is common for thermodynamics, and you can prove it. I think you did it before, so I don't want to do the proof. You can prove it by simply differentiate this by with respect to lambda. Okay, the first line here. Okay, now why is it nice to have this this kind of theorem in thermodynamics? That's because in thermodynamics we talk about extensive and intensive variables so much, right? So you see, this is this lambda is a factor that you can use to change the system size. Okay, so that is to say, if you can find and some independent quantity x, y, z that you can scale by the system size. So lambda is what I want to use. When we come back to thermodynamics, lambda is a factor to change the system size. It's a factor to change the system size. I can double it, I can halve it, I can do what, I can make it 100 times bigger, it doesn't matter. To change the system size. And it's so common in thermodynamics, it turns out that this problem is precisely applicable to our situation here. Okay, so let's check. If I take this U, okay, I want to evaluate this. So if I take the U, if I take a system of volume, original volume, V, right? So originally I will have U would depends on S, V, and Ni. And now I ask you, I demand this to be, I'm going to take the same system and make a copy. Okay, that is to say, I'm going to make a copy and put it side by side. So I'm going to double the system size. Or I can make lambda copies. And because this is extensive, so once I do that, my internal energy will depend on lambda times S. Okay, and volume, I make lambda copies. So the volume will scale by lambda V. And I take the same system and I make lambda copies. So of course, in the end, the total system will have lambda times Ni particles. Okay, and I have lambda copies. Each of them will have originally will have internal energy U. So once I finish this operation, of course, my internal energy will also be amplified or multiplied by the same factor lambda. Okay, so it turns out that this is really what we want. So this U is a homogeneous function of degree 1. Okay, so this is true. This is true. Therefore, U is a homogeneous function of degree 1. Okay, so all the hard work, actually, there's no hard work to do. You can just write down this line. So U okay, here. And therefore, U is originally is S. So let's write S. And this is the partial derivative of U with respect to S. So you have this. And then you have a lot of n terms. So let's write the sum. And for the ith constituent, I will have Ni partial derivative of U with respect to N sub I. And keep S constant, B constant, N, K, which are not I, constant. Okay, so you have achieved your goal. Look, I hope you appreciate this. I hope you realize that my aim is to get U. I like to have DU, but I also like to have U. So I know what U depends on explicitly. Okay, and how do you get all this derivative? You go back up here. Okay, I'm going to go back to the slide and tell you where to get. And this is partial U, partial S. What is this? So you go back here, right? You know from the fundamental treatment of differential, you know this prefactor is related to that. Okay, partial derivative of u with respect to s, keeping everything else constant, will give you T. Okay, so this first term here, this is just T. So this is temperature. And this, be careful, be careful, be careful. This is P with a minus sign. And here, this is mu I. Okay, so this is just Ts minus PV plus sum over mu I and I. Okay, this is cool, no? Is you get this very quickly. But there's a reason why I want to discuss this right after talking about phase transition. The reason I want the expression of U is because I know how to manipulate this expression to get the Gibbs function. Okay, so open system here. Okay, let's come here. This is enough. So Gibbs function G. This is the extensive quantity. Okay, these are all extensive quantity. Yeah. Sorry, this extensive quantity, extensive, and then there are two intensive quantities here. So I want to discuss the Gibbs function in the extensive form. Okay, this is U minus Ts plus PV. Okay, this is Gibbs function. And it turns out to be related to this, right? Because if I rearrange this, I will immediately get the Gibbs is just sum over I, mu I, and I. Okay, so actually this is the result. I want to box. Okay, so this gives you another view to deal with phase transition. You could also discuss a phase transition like this. You can treat your phase transition as your system as composing of subsystems that can exchange particle. So if you just look at a subsystem, for example, your liquid, you can view it equally like this. You can view your liquid as a system which is open. Okay, the total system can be closed, but the subsystem is open, so you can introduce the chemical potential that way. Okay, so if I indeed do it this way and go back to the case of having only one type of particle, let's say I don't have electron or hole, I don't have oxygen mixed with nitrogen, I just have one type of particle to deal with, water molecule. Then in this case, my M is 1. M is the number of different types. So I don't have to sum. I sum from 1 to 1, so I only have one term. So if I have only one, so if only one type of particle, e.g. water molecule, then I will have G will be mu n. Okay, so this mu becomes G divided by n, which is what we used before. Okay, so this is chemical potential. There's another way of saying things. In the note in chapter 6, I say something like this without elaborate that. I say chemical potential can be, Gibbs function per particle can be regarded as chemical potential. Okay, so when we treated when we did the phase transition to get the phase boundary, we did something similar. We used the mass, but now if I just use the particle, and I can actually interpret my specific Gibbs function as chemical potential. And therefore, along the phase coexistence line, phase coexistence line, I can write mu1 is the same as mu2, the neighboring phase. Sorry, so I don't want you to get confused with this label. So I can write mu A is the same as mu B. So this is the same type of particle, but different phases. So for example, liquid water, a liquid H2O, and solid H2O. So this is along phase coexistence line of phase A and B. Let's do it this way. Okay, so that is the message I want to deliver. Okay, we did it without developing this chemical potential, but then you can also do it this way. Some books prefer to have a chapter or have an introduction of the open system before they talk about phase transition, and we do it the opposite way, but that is okay. Okay, the other thing, the last thing you should pay attention is this quantity is automatically intensive because of this. Okay, so please do not divide again by the system size. This is already intensive. Okay. Why? Okay, so let's move on and talk about other systems. This is a fun one. This is let's say we take an elastic rod, something that we can analyze using what we've learned so far. Very quickly, you will see why this is fun. Okay, so we have talked about PV system. So we are going to talk about another thermodynamic system. We are going to talk about two. So let's begin with this. So as usual, you start from first law when you have a new system. So here we are going to write the first law for you, plus d bar w. Okay, for the d bar q term, you don't have much choice because we still want to know what happens to the temperature of the system. We are talking about thermodynamics. And the conjugate variable is entropy, so we write it down. But now this is the thing. How do you deal with the work? If I have, let's assume here, the dominant way to perform work is by you take a piece of wire, elastic rod, elastic wire, and you pull on it. You apply force, you pull on it. So there will be a tension. And when you do it, your rod and your wire can change length. Okay, and this is the easiest way to understand the work done, right? So if you pull on it, the wire becomes longer. The work you introduce will be given by F, which is the tension, times the infinitesimal change of the length when the wire is pulled, is stretched. Okay, so this is the tension, this is the tension, and this is the response to that tension. So this is the length, and this is infinitesimal change of length. So I think I hope everybody is really with me. The funny thing was once when I was giving this lecture, some student drifted away, maybe sleeping, fell asleep or whatever. And then that student thought this is latent heat, this L, and then got completely lost and asked the question. So usually there's no stupid question, but there are always funny question, and that was a funny question. Okay, so next, let's, so this is length, okay? This is length, dl, not latent heat. Okay, so let's define this, dl divided by L. We are going to talk about a situation which is 1D. So this change of length, normalized to the original length, this is called strength. And here, this is really a unique axial strength. Is usually given like this, or simply, this is a fractional length change. Okay, and this wire will have a finite cross-sectional area. Okay, so if I should maybe emphasize this, we are going to apply the force really like this along the axis of the wire. So this is the cross-sectional area A, cross-sectional area A. So I'm going to pull like this. Okay, so I'm going to assume mainly the dominant deformation is due to the change of the length. Okay, so you can also argue that what happens to the cross-sectional area, but we are not going to worry about that. What we are going to extract is the length change. Okay, so if you have this stress divided by area, sorry, the tension divided by area, this is the stress. Okay, this is the cross-sectional area. So from here, you know, if you have stress-strain relationship, you can define an elastic modulus. And the appropriate elastic modulus here is isothermal Young's modulus. So I'm going to use the notation E. I will put this T to remind you that I'm talking about isothermal case. Okay, so this is stress-strain relationship. Okay, so something that is useful for me when I learn this kind of thing is to always remember Hooke's law. What happens when you have a spring and you have a deformation to discuss, you have a force to apply, and what is the elastic constant. Okay, this is more general than that. So this is isothermal Young's modulus. Okay, this turns out to be L over A, partial derivative. Okay, so this is what I want. In the end, I want to have this partial derivative to work on. Okay, why is it df over A, not f over A? That is because I want to discuss infinitesimal change of the force. So I can sum them up later. Okay, and then the other thing is I want to get this partial derivative that I can change. Okay, I'm applying a tiny force, and that will be my stress. And then the rate of change is given by this. Okay, so now we are not there yet. We still have a few notation to introduce. So I'm going to introduce alpha. Okay, and this alpha is related to the beta you use in your assignment in earlier parts of the course. So this is about the linear expansion coefficient. So I'm going to have the linear expansion. Sorry, handwriting. Linear expansion coefficient. At constant tension. So this is this describe how readily the length of the rod will change when temperature is varied. So this is okay. Okay, let's write a bit. How readily the length changes when you change the temperature. Okay, so this is defined as how readily the length will change when you keep the constant tension. Okay, and we don't like this as usual. We don't like this. We like this to be a fractional change. Okay, so that's why there's a 1 over L. Now you might find this is crazy. This is a new definition, but no, this is actually very similar to what you had before. So if you look at what we did for the PV system, you know, you define the beta. If I have a volume PV system, we have something like that, right? We have 1 over V. This beta is related to the expansion coefficient, but it's due to the volume. And you know you can write something like this. So this is the isobaric case. And how do you imagine this? Actually, this is not too difficult, right? How do you keep the constant tension? For example, I take a piece of wire, I hold it, and I can put some mass at the bottom to keep the tension constant. Okay, so you have seen this similar mathematical form before, but this is for the PV system. And there, the intensive variable P serves like a force, and this is really a force. So this is not too surprising. Okay, and now this is the fun thing. When it comes to here, you see, so far I have alpha F and E sub T to worry about. So we need to discuss the sign. I think this part, the rest is really just you do this mathematics again and again. But the fun thing is to discuss the sign of these quantities. Okay, so ET, E sub T is always positive. When you pull something, it will become longer, right? When you pull something, it will become longer. Okay, so or you can imagine that to be the reciprocal. But anyway, when you put the force, length will increase. Okay, so this is always positive. So pull something. You pull the wire, it becomes longer. Okay, what about this alpha F? This is the fun bit. So alpha F can have either sign. Can have plus or minus. Okay, so usually, I say usually, for most metals, the thermal expansion coefficient, this coefficient is positive. And for rubber, this can be negative. Okay, that is to say, if you try to heat, try to raise the temperature, rubber actually shrink. Okay, so this is fun thing. Okay, there's more to say here. What is the time? Okay, now I propose something here. I propose a break. I'm going to burn some rubber in my office to show you that really I can find you this situation. Okay, so to do that, I don't want to keep the video. So I'm going to switch off the video and then let you see me. Okay. Okay, welcome back. I think now you are convinced that we can have a different sign for rubber. Okay, so what do we do here? Look at this. We have partial derivative of F with respect to L, partial derivative of L with respect to T. We can ask one more question, actually. Now, the other question, I think it's kind of intuitive for you to interpret all these partial derivatives. Okay, the next one, we don't need this heading, right? I will add one more, delete this. Okay, the next question you can ask is the following. If I have, suppose I do something like this. I have two rigid walls. And then I put my wire like this. Okay, being rigid, then I will have constant L. Okay, so this is a rigid wall. I can ask about something else. You can kind of guess already. Look at this. What do we have? What are the parameters we want to analyze? We have F, we have L, we have T. Okay, so we already have two differentials, sorry, partial derivative. One is constant T, one is constant F. And now the next one is constant L, which is something you can also ask. So you can ask yourself, what is this quantity? Okay, if I have constant L, what is the change of the tension when you change the temperature? And this is, for some of you who play musical instrument, this might be quite intuitive to you, right? Because let's say you have your guitar. You will fix a string like this, and before you play, you have to tune the guitar. And then maybe you tune it somewhere very cold, and then you walk outside to play, which is the temperature difference may be significant. And you find that you have to redo the tuning. And that is this quantity actually. So that is the change of the tension, which will give you the different pitch with respect to the temperature difference, although you keep the string at constant L. Okay, so this is the quantity you can ask yourself. This is also another, the quantity of interest is of interest too. Okay, so the picture is given here. Okay, how do you analyze this? Okay, quick. Can you tell me, if I want an expression for this, how do I get it? Suppose you already know the rest. Hello. I have, yes, thank you. It's the reciprocity theorem. We're talking about three partial derivatives. each with different variable kept constant. So you should know this is reciprocity. Okay, so I will just write the result now. You can apply reciprocity theorem. Thank you. And you get this result. So this is, I will just change it to the other side. Okay, this is the ratio of this to this. Sorry, okay, I will just write it as product. Okay, is it correct? Right, this is reciprocity, but I write it in maybe in a form that you might not be familiar, but this is it. Okay, you already know this too, because we manipulated these terms before. So that is to say, I can rewrite this in terms of Young's modulus and this linear thermal expansion coefficient alpha, right? This is related to alpha F. This is related to E sub T with some term in front, maybe a L here, and this one will have area involved. Okay, so just trust me, you can verify this yourself in 1 minute. This is the end result. Okay, EAL. Okay, so again, if you have different sign, then this is kind of important, right? Again, let me remind you that this E sub T is always positive, but this one can change sign. So when you pick your musical instrument, suppose you are using different materials for the strings, then the change of temperature will give you the opposite effect. Okay, so the tension in metal wire will go down with increasing temperature. Okay, why? Now, for metal, E sub T is positive, this is positive, so this partial derivative is negative. Okay, so if you increase the temperature, tension will go down to give you a minus sign. Okay, and maybe this is, I don't play musical instrument, but someone who can play the instrument can tell us whether this is the experience. Okay, so, and you get the opposite effect if you have rubber. Okay, so this is one thing we can ask, but there are more we can ask. Something I want to really answer is what happened to the entropy. So here, how do I get entropy? I'm going to write the Helmholtz function. Okay, this is the definition of F. So dF is the same. You write the same du minus TdS minus S dt. But the TdS term will cancel as before. But now you have S dt minus S dt. The work term becomes FdL. So this is the differential form of F. Okay. And I want to discuss entropy, so I need to bring in Maxwell's relation. Because, why do I do it this way? Because I want to link it again to the parameters I know. There's a reason why I introduced this. It's not because I really want to discuss music, but really I want the Maxwell relation. Very quickly, I can write this down. This partial derivative at constant t. So I already, what is this? This is the partial derivative of f with respect to t at constant L. Okay, and I can differentiate this again at constant t, but with respect to L, there's a minus sign here, which I will move to the other side. Okay, this is the Maxwell relation for this scenario. So what is the other mixed derivative? The other mixed derivative will be the partial derivative of f. This here is already the first derivative was with respect to L, so the second derivative has to be with respect to t, but keeping constant L. Okay, so this is hopefully this is not a problem for you. In the PV system, we have done so much. Okay, so this is Maxwell relation is coming from the fact that the mixed derivatives must be equal because f is a function of state. Okay, so once I write it this way, you recognize this. This is the question I asked earlier. It's the same partial derivative, so I can just copy, but with a minus sign in front. Okay, again, this is a very interesting scenario because whether the entropy goes up or down when you pull depends on the material. Even though you are talking about the same shape, but then when you pull, the entropy can be very different. The change of the entropy can be very different. Okay, so here, let's look at rubber. Rubber, so for rubber, Et positive, alpha F positive. Okay, so the entropy of rubber, S, of rubber wire, so these are all about rubber. When you pull, S decreases, right? Nobody correct me. Not good sign. Are you following my lecture? Or so for rubber, E sub T is positive and alpha is negative. So I have this whole combination is a negative quantity. So when I pull, when I try to increase the length, entropy goes down. So S decreases when the rubber wire is stretched when you pull on it. Okay, can you do one experiment on this? Do you know how to verify this? This is another experiment that doesn't require you to burn things, but it's something you can try to do at home. Okay, now this really tests your understanding about this whole notion of thermodynamics we developed so far. Okay, so when you pull a rubber wire, entropy decreases. What does it mean? How can the entropy decreases? How can the entropy of the thermodynamic system, which is your rubber wire, goes down? And this can happen when you have some heat flowing out to the surrounding, from the system to the surrounding. Therefore, you can do one experiment like this. You take a rubber band, a rather big one, so be careful. Take a thick one, don't take a very tiny one. You prepare yourself by, you cut the rubber band. So you take a rubber band usually like this. You cut it, a rather thick one, so the effect is easier to notice. And then you use your fingers on both hands, and you pull very quickly. And when you pull very quickly, this physics has to happen. Okay, doesn't need to be quickly, but quick so that the thermodynamic system doesn't have time to reach thermal equilibrium with the surrounding before you finish your experiment. So you pull, right, quick enough, so you will have a rubber band which is hotter, and then you put it on your lips. That is where you can feel the sense the temperature. Okay, so you pull, quickly pull on the lip, near your mouth, put on the lips, and you will feel that this is hotter. Okay, and this is something I encourage you to try. Okay, and don't take something too small, because if it breaks, it will hit on your face, and don't come to complain to me about this. Okay, so this is for you to verify, and all this come from simply manipulating the work term for the first law, and you get all this physics. Okay, so this is what I need to talk about the rubber band, elastic rod. So next, I want to switch to another thermodynamic system which we can really analyze in a very similar way and get something meaningful. And that is the magnet. I'm going to talk about a paramagnet. So magnet, of course, is complicated, but we can look at the simplest case. So I would tell you the assumption here. Okay, here the similar situation is such that you need to manipulate the work term. So in general, we will write the work like this. So if you have a paramagnet, which will give you the magnet contains magnetic moment that can interact with the external field, you will write the work done like this. So I'm going to, why do I say magnet is complicated? Because in principle, all these moments can feel the magnetic field generated by other moments. But we are not going to treat this kind of complicated situation. I'm going to simplify to the case that my magnetic moment, I'm going to only discuss the moment that will align in the magnetic field, and this magnetic field is the magnetic field you apply. That is to say, I ignore the difficult problem of interaction between my particles. So this is a non-interacting system. When we do statistical mechanics, we are going to look at the magnet again. And there we are going to also consider only the non-interacting case for this course. Okay, but you will see how much you can already gain from this. Okay, so this is the work term that we need to modify. We don't do PdV, we don't do FdL, we are going to do MdDB. So I don't even want to consider the general case of having this dot product. I'm going to only consider the case where the moments are aligned or anti-aligned. So I will reduce the dot product to scalar product. Okay, so this is the case of non-interacting magnetic moment, magnetic moments. Arrange in the lattice, arrange in the solid, in the lattice of a solid. So we are going to consider this situation, and then we are going to use the magnetic field to manipulate this. So we are going to, I need to be a bit more careful about the field, because you know from E and N, you have B field, you have H field, you have magnetization M. So this should be carefully distinguished first. So I'm going to apply field. This will causes the alignment. of magnetic moments. Okay, so what is my first law? My first law, du will becomes TdS. As I say, I don't want to worry about the general angle. I'm going to consider the simplest case of having parallel or alignment or anti-parallel. So this is the first law. Okay, I use the field, I use B, this symbol. Okay, but this, okay, this is really, if you want to be very precise, this is called magnetic induction. And the applied field is H. So whereas H is really the applied field, the one you read on your power supply. For example, I have a magnet which I bring to the lab, and I apply some field, and that is this H. This is the applied magnetic field. Okay, and the two are related like this. So the B is related to H by mu naught, H plus M. Okay, so H really is the applied field, B is the magnetic induction, but I'm going to use, I'm going to just loosely say this is B. The reason I can say that is because M is very small, much smaller than H for a paramagnet. Okay, so I'm going to only consider, so for a paramagnet, M is small. How small? Compared with the field you can apply. Now, if M is comparable to H, then when you discuss material property, you need to really consider this, right? The magnetization due to the alignment of the moments. Okay, and therefore B is approximately mu naught H. Okay. Okay, so here this is a lowercase m. This is a capital K. This is a capital M. This is uppercase. So this little m is related to the capital M by a volume factor. Okay, so this is volume, and this is called magnetization. And this is really the moment. Okay, so magnetization is the total moment per unit volume. Okay, so this is a M with a base like this. Okay, maybe I can write it here. Okay, I want to define another quantity. Now it's just definition. Once we get all this done, we can launch very quickly. So magnetic, when we talk about magnet, it's very common to define a quantity called the magnetic susceptibility. Susceptibility, chi. And this tells you how easily it is to induce the magnetization with a given magnetic field. That is why it's called susceptibility. If a material has high susceptibility, it means it's very susceptible to the application of the magnetic field. So you will have a larger magnetization even if you apply the same field. Okay, and this is defined this way. So this is M divided by H, and usually we take the low field limit. Okay, what we really want is to discuss a magnetic susceptibility without saturating the moment. Okay, we don't want, if you apply very, very high field, you can actually polarize everything, all the moment, and then there's no more, then we cannot discuss the change anymore. So we are more interested in the low field limit. Okay, and because of the equivalence between H and B, magnetic induction and magnetic field, so we can write mu naught and B. I think now if you see this very sharp corner, this is capital M. Okay, if you see a very round, there's lowercase m for moment. I think it's kind of clear. This writing is not too bad. Okay, so did I write? What did I say? Okay, this is M. Okay, I will tell you the result without proving. But you can get some intuition. Chi, we want to care about, we want to ask what is the temperature dependence of chi, the susceptibility. And this is 1 over T. Sorry, this is proportional to 1 over T. 1 over T. Why do you have something like this? Now, this is a little bit extreme. This is from Blundell and Blundell, but it gives you a good picture to imagine this. Now, what you really want to do with the magnetic field is to align the moment, right? Now, if I want to, the role of this magnetic field, the magnetic field will try its best to align the moments. This is what it wants to do. But when you have high temperature, when you're at high temperature, you have thermal fluctuation. When you try to align the moment, you are competing with the thermal energy, which try to randomize the moment. And therefore, if you want to have high magnetization with the same magnetic field, you run into trouble at high temperature, because at high temperature, your thermal energy is acting against you. And that is why you have this 1 over T dependence. And this is something we can justify quite well when we do statistical mechanics. You will see this form again. But now at the moment, you need this intuition. Okay, this is due to because of the thermal fluctuation. Thermal fluctuation tends to randomize magnetic moment, right? So when you have high temperature, you have more thermal fluctuations. And if you have completely random moments, you have like very high temperature, you have 0. And that's why you have this 1 over T dependence. Okay, so now we can already write the first partial derivative that we will need. So the partial derivative, this partial derivative, at constant B even, will be negative. This is what we can say. Without an explicit form, we cannot say much, but we can at least discuss the sign. Just like when we discussed the sign of alpha F earlier. Okay. By the way, when we talk about this rubber, I told you when you pull on the rubber, the entropy goes down. I didn't explain why, but I would ask you to think about why this is the case. Right? When you pull, when you take a rubber wire and pull, entropy goes down. There's a very nice intuition similar to this that you can discuss. Okay, so that you can think about it. Okay, so we get one sign of the partial derivative. This is due to Curie's law. What is the next one? Okay, here. Next. Okay, so let's move on and write Helmholtz function. The reason is very simple. Why do I keep writing this function? Because I want to get the entropy change. So this is a df is du minus t ds minus s dt. So just to remind you, f is u minus ts. Okay, so my df for this case will have tds becomes s dt with a minus sign, and then the work term will remain, but with a minus sign, minus mdb. Okay. And the Maxwell relation is the next. Maxwell relation. Following the same logic before, I can extract the change of the entropy when I apply a magnetic field. Right? So this is already this is the mixed derivative. The second derivative I have to differentiate with respect to this quantity and keeping this quantity constant. This is this B. Okay, and I use the definition of magnetization. This is moment. Moment is volume times magnetization. So I'm going to bring this volume in, and I'm going to assume volume doesn't change. So let me write this first. This is M again. Okay, so you see, this is big M times V, but I pull this V out because I assume V to be a constant with respect to T. Assume it to be a constant, and this is a fair assumption in the region of interest. There is solid at low temperature. So solid at low temperature, you know, things will, the volume will indeed change when you cool down. This is thermal expansion, but thermal expansion will slow down at low temperature. So this is a fair assumption, particularly fair assumption for solid at low T. And indeed, I'm going to focus at low T later. I'm going to stick to low temperature and discuss cooling. Okay, so so from here I can write the change of entropy with respect to field at constant T is this thing is V sorry, I don't want to correct that. The V. And what else do we know? Now this M is related to the susceptibility, right? So here, this M is related to the susceptibility, and we know the sign of the susceptibility. We know the sign of this differential. So we really want to bring this out. Okay, so magnetization is related to susceptibility, and we know the sign of partial chi, partial T, which I justified earlier. So I'm going to bring this out for you. Okay, so this is positive, and field is positive, and this will be negative. Okay, why? This is due to Curie law. Did I write Curie? This, by the way, this is a famous law. This is called Curie's law. So this minus this negative sign again is due to Curie's. Okay, just like the case of rubber band, we want to discuss this kind of thing. This is really something we are interested. Now, the entropy change is negative. When you apply magnetic field, when you increase the magnetic field, entropy goes down. Okay, isothermally. Okay, if you do this process isothermally, here maybe it's not surprising to have the intuition. You can actually use the same picture here. Just use this same picture. Okay, so when you do not have magnetic field, if your magnetic moments do not know the neighbors, do not know any friends, then there's no driving force for the moment to align. There's no reference. It's just when there's no magnetic field, it will just feel that all orientation is the same. Okay, so this is a very random situation, and your moment can equally point along any given any direction it likes. Okay, you pick a moment, there's no preferential direction, and therefore if you look at these moments, it has a lot of freedom to explore. Okay, so you are, let's say you have entropy, some fixed amount of entropy at this point, and now you apply magnetic field. When you apply magnetic field, suddenly all these moments realize, there's a direction which I should go. Okay, and these will make the moments will tend to align with the magnetic field, and when you increase the magnetic field, this tendency will get higher, and therefore with the larger magnetic field, the moments will have less desire to explore other direction except the direction of the magnetic field, and therefore entropy goes down. Okay, so this is this picture here. Okay, so now you should consider all this. You should consider this term and compare with the case of the rubber band. When you pull, entropy goes down. And then more importantly, you should think even deeper and go a little bit further from here. Think about the gas again. If you have isothermal expansion of the gas, what happens to the entropy? Does it go up or down? All this can be discussed, and they can be discussed in a very similar way once you know how to write down the first law, the Helmholtz function, then the Maxwell relation. You can unify all this, and in fact, in Blundell, there is in the end of this relevant chapter, there's a picture showing these three cases. Okay. So if I have an isothermal reversible increase of field, if I have something like this, entropy goes down. By the same argument, there must be some heat release. This is like the rubber band I asked you to do, this experiment I asked you to do. Entropy goes down. If you very quickly go and feel the system temperature before it has time to reach thermal equilibrium with the surrounding, you will feel the rubber band is hotter. So heat must be released from the system. And here you have the same thing. You have the heat released from the system, and this can be this heat release can be calculated. Okay, so this is simply due to this term. You have this differential. And then you have delta B here. Okay, and then you have T like that. Okay, so this you can see that this is, you see this is TDS. This is the unit of heat. Okay, and this is suppose you increase the field of the system, then this is the relevant equation for you to calculate. Okay, let's quickly plug in everything, and you can get what you want. So what do I want? I have this mu naught and then P and delta P. Okay, so if you increase the field, this term is positive. Everything else is positive, 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 and this term is negative. And this is exactly what I said. If you increase the field, you get delta Q, which is negative. Okay, so this is captured fully by this expression. Okay, I think we are ready to talk about cooling, almost. There's one more partial derivative of interest, and that is this quantity. Now for cooling, I need to introduce this. Look, what is the variable that is kept constant? That is S, entropy. Okay, so to get this, we use the reciprocity theorem again, reciprocity theorem. To relate this to the partial derivative we developed so far. So we have seen this one, isothermal change. And then we have seen this. Sorry, we haven't seen this, but I need to define this for you. Okay, so reciprocity will give you this relationship. So this is what we discussed earlier, and this is something new. Okay, so I'm going to multiply by T. I'm going to multiply this by T, and then I'm going to multiply this by 1 over T for the second one. Okay, the reason I want to do that is because I want this TDS. Okay, so what do I have actually from here? This is related to heat capacity, TDS divided by dt. This is heat capacity. Okay. So this thing is 1 over heat capacity, but heat capacity at constant field. Just like for the PV system, you talk about heat capacity at constant volume, at constant P. This is not a PV system, but a magnetic system. Then you can have a heat capacity with a constant field as the constraint. Okay, and this is this term here. Sorry, I should. And then the rest is given here. This thing here. Okay, it's coming from the Maxwell relation. All right, so from here you get here, from here you get here, and from this you get this. Okay, so the result will be temperature times volume times field divided by mu naught and this. Okay, and now again we discuss the sign, because there's a minus sign here. This thing is minus, is negative. So the whole term, the whole product will be positive. Okay, so this provides the basis for cooling. Now, the key is to realize this is positive. This partial T, partial V is positive. I would like to continue if possible. If you need to leave, again, please don't worry, just leave and you have the video. Okay, I'm nearly done with this cooling. What I want to share the story is how do you cool to very, very low temperature. So this is the physics we discuss here. Okay, and this is called adiabatic cooling, adiabatic demagnetization. So what do we have? We have this partial derivative. Right, this is what we discover right here. Right here, I just copy for you. Right, and then we also have another one, the isothermal one, which is this. This is even earlier. Okay, this is related to how you align the moment, the second partial derivative, and the sign is negative. Okay, now this is the cool thing. Now, suppose you know how to calculate the entropy as a function of temperature. Suppose you know how to do that. And this is, for example, if you know the system very well, you do very good statistical mechanics, you can do this. You can calculate this. Okay? Suppose you know that. Let me take you through. This is a series of, this plot is prepared in such a way that you plot S versus T at different magnetic fields. So each line represents different magnetic field. Okay, and this plot is consistent with all these partial derivative and with a lot more detail because this shape is very particular. This is because, as I say, the calculation was a realistic calculation. Okay, this is from Blundell and Blundell. Okay, but here we can already know how to do cooling. Why do we want to do that? That is, the reason is the following. Suppose I want to do low temperature physics. I want to do cooling. I want to cool my system to very low temperature. But I only have liquid helium. So liquid helium, I will start at the initial temperature of 4.2 Kelvin. This I is initial. So you ask yourself, is there a trick for me to cool below 4.2 Kelvin? Yes, of course, the answer is yes. Otherwise, I wouldn't present it here. The answer is this. This is the answer. This is called, you cool by magnetic field. This is adiabatic cooling. Okay, so let me tell you how to do this. So first, you start at 4.2 Kelvin. You cool your system with liquid helium. For example, with liquid helium, you can reach this, no problem. You reach this. This is your initial state. You prepare your system by following this path. At this moment, you are at zero field. Now you apply magnetic field to some finite value labeled by B sub B. Okay, so this is an isothermal experiment because you are traveling vertically in this ST plane. So you do now this AB, let me write this down, this A to B, what are you really doing? You are doing isothermal magnetization. So you increase the field to induce the magnetization, but you connect your experiment to the liquid helium heat bath. So you can maintain the constant temperature because of the bath. So this heat bath, just imagine this to be a reservoir. So how can you have heat changes but still keep the temperature constant? The reason is very simple. You have a huge reservoir. Okay, and this reservoir is liquid helium. So you have isothermal magnetization. So this is to prepare your system at the lower entropy state. Look, here this is S, so entropy is higher, this entropy is lower. I already discussed the physics, and this is due to this partial derivative. Okay, you align the moment, you enter a lower entropy state. Okay, 2, you move from B to C. This is called the adiabatic demagnetization. Adiabatic demag. Magnetization means you increase the magnetization, and demagnetization means you decrease the magnetization. And look what you are doing. You are going to do this very slowly from here to here. That is to say, when you reach magnetic field B sub B, you are going to reduce the magnetic field to 0 in a very slow manner. So at any point in time, you are maintaining a quasi-static equilibrium state. That is to say, your entropy change is 0, so you are traveling horizontally. Okay, so once you do this, you see you are traveling horizontally, such that you are reaching lower and lower and lower and lower and lower and lower and lower magnetic field. Eventually, you reach 0 field. And look what happens at 0 field. You are at the lower temperature. So T final is lower than T initial, and you reach cooling. And that is the second derivative, partial derivative. So maybe a color code this. So the relevant physics is here. So this one is this, and this one is here. Okay, so you reduce the magnetic field, you reduce the temperature at the same time. So this is positive. This is correct. Okay, this is a very useful stuff. For example, I say liquid helium, and how do you achieve this in reality? Let me, I have discussed the physics now. So next I want to discuss, I want to just present some realistic cases for you. How do you do this kind of experiment? Now this is your paramagnet. So this salt, what is the salt? This is the magnet, paramagnet. Okay. So this thing is inside a chamber which you can pump. You see, there's a pump. So how do you achieve isothermal case? To do the isothermal magnetization, you put helium gas inside this chamber. Okay, so when you put helium gas, all this helium gas will serve as an exchange gas. So you will maintain the thermal link between the magnet and the buff. That is how you achieve the first segment A to B at the same temperature. So this is because helium will give you 4.2 Kelvin. When you have exchange gas, it will just thermally connect the buff to the salt. So you can maintain the constant temperature. Okay, and once you reach the magnetic field, this is the magnet, you reach the final magnetic field you want, you pump away all this exchange gas, so you thermally isolate this, right? So this is your universe. You do not have any thermal coupling with the buff anymore. So this salt itself is your universe. And then you do it slowly and make sure this is reversible. And this is essentially saying that you are always having the state of ds equals 0. And that will allow you to reach a lower temperature compared with the outside world, which is the helium. Because you do not, after all, you don't know the existence of the helium buff anymore. You pump away the exchange gas. And if you put your experiment on, you attach your experiment on the salt, you can do low temperature experiment. For example, you put your superconductor here, you bring some wires, you can do measurement here. And that will give you temperature lower than the buff. Okay, finally, I show you a more realistic case. This is something I used when I was a student, PhD student. This is this paramagnetic salt. This is what we call this is our thermodynamic system. And usually we have an experiment that we put it here. And this is the design of the cryostat with a lot of wirings, a lot of tube for pumping, and the whole thing goes into the bath. So this shiny thing, inside this shiny thing you have liquid helium for maintaining 4.2 Kelvin. And to save helium, we also have another layer of liquid nitrogen to serve as a thermal jacket, and all the experimental setup are here. Okay, that's all for this part of the course. Okay, and on Wednesday we talk about the third law very quickly. Then we are done with the thermodynamic part. Okay, so on Wednesday we will definitely start statistical mechanics. We will have to learn how to do counting. Okay, thank you very much.